Hello, gentle readers. December 29th, 2024. From a desk with Ross Finlayson here in Seattle, Washington is Logos 2000. A study in the foundations of physics, logics, mathematics, science, for reason, philosophy. That foundations is the idea that there's a good theory, and so if it's good enough for anybody, it should be good enough for everybody, at least insofar as these objective types of things go. And then as with regards to the language that can be expressed in, it's just like anything else. All or each of us, intersubjective beings, thinking beings, feeling beings, sensory equipped beings, have that each have their own philosophy, each have their own psychology, each have their own language, and then as with regards to, yet at the same time there's attained to a great confluence of all the things which can be real, the inner objective, the objective and inner objective, and then these notions that make for truth, that it ends up being that it's kind of like a theory of physics where energy is conserved. It's a theory of logic where truth is conserved. And also that it happens to be all the things. Then as with regards to knowns and unknowns, certainty and uncertainty, and these kinds of considerations for the ontology, then as with regards to, for strong mathematical Platonism, that there is a real universe of mathematical objects, and it is perfect, and human beings are not necessarily, and kind of necessarily not according to the usual accounts, yet as well that it ends up being that there's one at all that we all attain to, and then with the necessary goals of not getting it wrong, or saying it's done before it's done, and these kinds of things, that the usual ideas associated with that are part and parcel of the dialogue of philosophical creatures in the technical philosophy, and for mathematicians and logicians and reasoning beings since antiquity and since prehistory, and then, for example, for thinkers like Derrida and Husserl at the turn of the 20th century, the fin de siècle, 1900 to 1920s, having arrived, then, after a strong course of scientism and logicist positive breaking off and breaking away from otherwise determinism and the causality of the world, which here is considered part of the strong mathematical Platonism, that then the return to this idea of the pre-scientific and then the pre-geometric world is this, after this axiomless natural deduction. It's the same one that people think about when they say, well, there is nothing, and how am I answering the fundamental question of metaphysics with geometry and proportion and words and like and different and these kinds of things. So not too much today, just kind of as usual course of just reviewing the stacks, whatever books might have arrived, and then to be looking through those, and then to try to pick up a trail, pick up a course, pick up something that ends up being interesting, hopefully, and it's not necessarily going to be interesting to everybody, and some of these talks are more conducive to being called like making a main point, and is a sort of a dialectical account, where others are more the rambling variety, just plainly expositive. And so by this I'm saying I don't really have much to say, that then as regards to whether it's all been done before and all been said before and these kinds of things, that very much so, mostly it has, and then that here there's ideas that are as from a 30-year study in foundations, it's pretty much boiled down to just putting continuity and infinity right at the start. That's been studied for its value, and then with relation to physics, that it's the sum of history, sum of potentials, which can reduce to sum of potentials, and then least action, least gradient, which can kind of reduce to least gradient or least action. I'm not really quite sure which one to say about that. this ends up as a principled sort of approach that all the mechanics of the statics and dynamics are all defined this way. Since the oldest rule or law of physics is what goes up must come down in a gravity well setting of the terrestrial. That otherwise it's about creation and destruction, and that there isn't any is the usual idea in theories with conservation laws. But then those events are always a constant interplay of creation and destruction vis-a-vis conservation. And so then here that's framed as that it really must be a continuity law, that a conservation law by itself is so in an instant in time, but we always have moment and motion. And so it ends up in resulting that points and instants in time have all their implicit dimensional quantities attached to them, even if they're dimensionless from the classical perspective, that they're dimensioned with regards to all the possible ways to quantify these things. And then it also relates as well to the implicit universal quantifier from logic, that in front of like a variable for comprehension and a quantifier saying like the universal quantifier for any are implicitly many, infinitely many more quantifiers for that one variable is everything. Vis-a-vis the idea is that it's only the least thing. So then there's that, and then for that disambiguating the universal quantifier as with regards to for each, for any, for every, for all is important when it comes around to issues otherwise that make arise the impredicative, which makes predicativity intractable or inconsistent and thus unacceptable for various reasons, for the rationality of the reason. Has it then once those things are sort of equipped and it's like always present and helping satisfy all these old pans, like the only constant is change, the origin is everywhere, and these kinds of things, that thusly it helps to advise, instead of just following the usual linear account, making the usual linear account. And so it and there's something a lot different, and it's been mentioned here a bunch of times about the prior and posterior analytics, that which is before and that which is after the prior and the posterior, that not having either one of those results only kind of at a halfway account. And so then for especially these infinitary completions, that it's necessary to have this wider, fuller dialectic, and that it's not so tough and it's not so bad. But then instead of having to kind of address the entire derivation and stack of the usual linear curriculum, says all the derivations and results, at least from my perspective, that I've ever wondered about, and from reading all these different kind of sources and considering how they're same and different, that at least then it's easy to have like a working theory that's flexible for pretty much all purposes, that suffices to, as it said for Aristotle, that Aristotle won't be fooled, and if someone else gets fooled with Aristotle's reasoning, Aristotle will be able to explain to them what limitations or implicits or unstated assumptions went into why there's a way to consider it more free of error, say. Let's see. Lincoln Barnett. Now I have something else by Lincoln Barnett. This is The Universe and Dr. Einstein, a readable book on Einstein's theories ever published. And so it's from Bantam Books in about the 70s, I imagine. First printing, 1948. Seventh printing, 1974. And so, taking a look at this today. He says he wants to thank his colleagues at Princeton and the Institute for Advanced Study, like Herman Weil and Robertson of the California Institute of Technology, commonly called Caltech. Thank Harlow Shapley of the Harvard Observatory and Havens of Columbia. So this was written in 1948, say. Forward by Albert Einstein. Anyone who has ever tried to present a rather abstract scientific subject in a popular manner knows the great difficulties of such an attempt. So here, as we talked about many times, there are differences between the popular accounts and Einstein's account, or for physics and the popularizations of physics. Because sooner or later, they'll be involved in a popularization or account, either inconstancy or misunderstanding, or a metaphor. And metaphor eventually fails. We have a strong idea of a strong metonymy, that our language, our kind of Coleridge language is called, is like it's a full natural human language. And it includes poetical and prosaical aspects to it. And then this Comenius language is like, that's the language with all the truths in it. And it's named for him, and he kind of theorized the existence of a thing. And it's kind of like Nietzsche's eternal text, that Nietzsche was so sad that he couldn't have, when really should have been happy, because there is one, and we can all attain to it. So when Einstein's saying here that it's tough to make stuff so for everybody when it's kind of a technical field, that includes ideas that A, his own understanding of it changed over time, and B, that as we've read here from Einstein's Out of My Later Years, that there's a certain particular approach and a very minimal kind of apparatus of what Einstein says is relativity theory, and that otherwise there's these other theories like electrical theory and mechanics and nuclear theory and these kinds of things. And then so he's had to protect himself from his followers and protect himself from otherwise people who followed his own theories and their developments, and those who take metaphors that don't make sense in the extrapolation. When it's kind of like when there's thought experiments that end up not applying, that then people will make their other usual inferences about the objects, the elements of discourse, whatever, in the thought experiments, whether it's the barn door and the telephone pole, or the rivets and at light speed and headlights and these kinds of things, is when they do and don't add up. And it's for something like curved space-time, is like, well, I meant it curves back together too, whereas otherwise people would say, well, it's just gone all over the place. And so that Einstein's saying that popular accounts are tough to get right, and that as well as like you kind of have to treat usual popular accounts as of popular, meaning the coffee table book physics of the day, is not necessarily correct. And so that's kind of what I'd be reading from Einstein's preface here to Barnett's book. Either he succeeds in being intelligible by concealing the core of the problem and by offering to the reader only superficial aspects or vague illusions, thus deceiving the reader by arousing in him the deceptive illusion of comprehension, or else he gives an expert account of the problem, but in such a fashion that the untrained reader is unable to follow the exposition and becomes discouraged from reading any further. See, now this is these are some examples of failure modes of trying to explain things, but then there are opposites of these, because sometimes people will understand when they detect that it's like, well, that metaphor that was given in the popular account runs out, so there's something wrong with it. So I know at least there's something wrong with it. I'm not stuck doubting myself when I can believe that there's a reason that that's dubitable, and so I don't have to worry about it too much. And the other side is when people's like, when you give an untrained person is like, well, here's the hard theory, and they're like, I don't get it all yet, but I know that there's the value in that. So at the same time, Einstein's saying this, like, it's tough to give good popular accounts, yet as well, these are the other reasons why everybody loves science. So many people really think that it's the greatest sort of thing, because of, as we've discussed here, there's like all that goes into the phenomenological and the as Aristotle put it, the joy of fulfilling the mental faculties, that it's kind of thing. then here he's also just kind of setting up that he's read this Lincoln Barnett's view, and so he'd probably be endorsing it in a sense. If these two categories are omitted from today's popular scientific literature, surprisingly little remains. But the little that is left is very valuable indeed. It is of great importance that the general public be given an opportunity to experience consciously and intelligently the efforts and results of scientific research. It is not sufficient that each result be taken up, elaborated, and applied by a few specialists in the field. Restricting the body of knowledge to a small group deadens the philosophical spirit of a people and leads to spiritual poverty. Lincoln Barnett's book represents a valuable contribution to popular scientific writing. The main ideas of the theory of relativity are extremely well presented. Moreover, the present state of our knowledge in physics is aptly characterized. The author shows how the growth of our factual knowledge, together with the striving for a unified theoretical conception comprising all empirical data, has led to the present situation, which is characterized, notwithstanding all successes, by an uncertainty concerning the choice of the basic theoretical concepts. So this amuses from Princeton, New Jersey, September 1948. And so this amuses me that Einstein is kind of writing in this manner. And from looking back on reading Einstein's Out of My Later Years, before it started getting ads attached to it and totally disrupting the flow of the narrative and the dialogue, that yet as well that it's a pretty good account, has that the conceptions or the basic theoretical concepts. Here's what I'll be looking to find out, kind of what's arrived then here in Barnett's text, is what's in with regards to Out of My Later Years. And so Barnett talks about, in the white walls of the Riverside Church in New York, the figures of 600 saints, philosophers, kings stand in limestone immortality. One panel enshrines the geniuses of science, 14 of them, Hippocrates to Einstein. In this whole sculptured gallery of the illustrious, Einstein is the only one who shook the world within the memory of most living men. Now, as I was acquiring this book, I conversed briefly about it with his seller, and we were talking about scientists. Because we were talking about Einstein, and then Feynman, who was for a while, was like, have you heard of any physicists? It was like, Einstein. It's like, how about another one? Well, what about that bongo guy on TV? Or Feynman, or then later it was Stephen Hawking. It was the robot voice guy. This is in some senses like a kind of a very only a Q value or public recognition rating idea of scientists. There's like Einstein is science to lots of people, and so then that said, I talked with this seller a little bit about the difference between popular scientists and other scientists, because when we were talking a bit about Stephen Hawking, he said, well, I prefer Roger Penrose, and I was happy that he was aware and familiar of this kind of idea. And then we talked about the popularizers who are great and important to help relay the wider milieu of science, like Tyson and Green and Kaku and Gribben and Barrow and a bunch of different contributors who are popularizers and scientists and philosophers and physicists themselves. Then as with regards to whether they're a bit more of kind of the crowd, as opposed to the developers, the innovators, as it were, and may so be. That Hawking is held up as for like after writing with Penrose to the Gravitational Research Foundation, or the GRF, Gravity Research Foundation. He won one of these essay contests, and because every year the Gravity Research Foundation has an essay contest, and anybody can enter. And it's not meant to be very long, and then the idea is that it's juried, and so they select a winning essay out of this every year, And so that kind of led to then Hawking, who has just like ideas all over the place. I mean, it's not like it's kind of like some people have a principle dogged course of like, it's all got to be consistent altogether. That's the approach here. And other people is just like, I'll pick up and put down any theory, and I can pick up and put down any theory, and all I have to do is make one thing that makes anything either contradictory or makes a numerical method for a solver, and that's doing physics. And it is, yet then somebody else has to figure out whether it's actually still correct, and that it's useful to hand to somebody else without it basically being easily wrong and this kind of stuff. So that then these were innovators in a sense. Then as with regards to what's enduring and coming out of that is like, well, the Einsteins definitely got this place all about relativity. And then Feynman's got QED, quantum electrodynamics, and all that kind of stuff. And Hawking has kind of got, well, it's like everything from that comes from like Bekenstein bounds and after Chandrasekhar, really, all the black hole physics. And otherwise, she's kind of a popularizer. And then later, here in the stack is some more of the book about what Hawking's efforts then came to be arrived at later into the 21st century. And we'll get to look in that a little bit. And this is kind of one of these subfields of physics. It's kind of things like after Higgs physics and so on. That's not really very compelling to me. It is what it is. It's about measurements and observables in high energy particle physics, about models of kind of the invariance in Noether's theorem, and compared to like something like Scheck's continuity transitions, which is here more apropos, because while symmetry breaking never happens, that's considered something in the mathematical model really had to have something about why that is so. For supersymmetry, that symmetry flex happens all the time. It's dynamics. It's change. It's part and parcel of the definition of motion and to do with mechanics. That here is considered as kind of like been gathering dust when all the higher energy glamorous front page particle physics activities are so many times just not really that compelling, and not really able to eventually be usable in a wider milieu, because they're just kind of, they painted themselves into the perfect corner and this kind of thing. So that's opinion, of course. And yet it's because it's a principled opinion, because here there's like a whole theory of axiomless natural deduction, axiomless geometry, making a strong mathematical platonism for physics that is a sum of histories, sum of potentials, least action, least gradient with a continuum, that anything without that is considered missing at least something. So it's talking about Einstein. And they're wondering about Einstein. A fellow wrote letters to a group of the nation's scientists asking them to submit lists of the 14 greatest names in scientific history. They all included Einstein. From 1905, when special relativity came up with also the optoelectron effect. It's like, remember electron physics? When Millikan measured the charge to mass ratio of an electron, I made photons the same way, and then that's what he won a Nobel Prize for. And then with regards to his theory of special relativity, it's like, remember Huygens' principle about waves, and then the one where he has constant light speed too. This one is just constant light speed, and then I have after this mass energy equivalency that kind of has to be derived one of three different ways at least from mechanics, and then also that the light speed as a constant has got three different ways to look at it from electrodynamics that happen to kind of point at the same value, but aren't the same things. But in some formulaic accounts, we can call it popular to say that they're the same thing. In fact, we're even going to give physics the idea that that's all the same thing, because that way they only need to know like 5 lines of algebra to then set up all the rest of the stuff to, given that we have a particular good lean and some good days, that it adds up all these different things. That here it's just kind of to pointing to the fact that then that sometimes the prizes are just like, they're not for like expanding knowledge, they're just for like closing a door of a little box and saying you have windowed and boxed the formula, and don't worry that it doesn't work on the edges or the outside. As long as you leave it in that box, it'll be well behaved and well posed according to Hadamard. And so that's the way of the things. And then the greater physics is like, well, what about space contraction and all that? It's like, well, you mean space curvature and the curvature of space time? It's like, well, yes and no. But then otherwise, we still want to have the super classical concepts to people, because it's like, how about immovable and unstoppable? How about these other ideas like Zeno's motion and arguments and the Achilles and the tortoise? You have to have these super classical concepts so that people can have the super classical notions of what otherwise are closed inductive inferences, dead ends, the inductive impasses, say, that cannot be crossed. The deduction arrives at crossing. These is among reasons why that the it's hard to find somebody who's won a Nobel Prize for something super classical. Yet there is stuff like asymptotic freedom, particle wave duality. We'd have to look at Allen aspect, but Bohm and de Broglie with the super classical wave, real wave collapse, and these kinds of things. Getting back to the deterministic, as with regards to that theories of just the abstract and then the loose, like multiple worlds hypothesis, or how about something else non-scientific, but just making for another bookkeeping dimension, or like clues of Klein. It helps to understood in that even things like this and like complex analysis are like not necessarily attachable and reattached to the physical model of the things. So it's kind of a hazard to leave that for people who don't know that, because it means space contraction, and it's kind of a real thing. And so after mass energy equivalency and a cosmological constant for space-time curvature non-zero, greater than zero, yet vanishingly small, it's like it's this least gradient. It's a least action and it's a least gradient. This kind of cosmological constant concept. That thusly this set the bounds for then, like, well, at least we can have, when you hold one of or two of these things constant with regards to mechanics, electrodynamics, and light, that it adds up, and according to a meter and a stopwatch. So carrying on here then, in the terrestrial setting, say. It is not surprising, therefore, that many college graduates still thinks of Einstein as a kind of mathematical surrealist, rather than as the discoverer of certain cosmic laws of immense importance in man's slow struggle to understand physical reality. He may not realize that relativity, over and above its scientific import, comprises a major philosophical system, which augments and illumines the reflections of the great epistemologists. So here, that's kind of part of the consideration of the course, is like, in the reading from Einstein, it was like, he's a model philosopher and he's a model physicist. They're two different things. And here, reading from D'Espagnat is like, we got to bring philosophy and physics back together, and because we're realists. And then that having a surrealism is an important matter of personal objectivity, to be able to maintain a reasoning apparatus, to always have the ability to think about something, even if it can't be really picked up or put down. Einstein, and so this is writing posthumously, I guess, spent the last years of his life working on a problem which had baffled him for more than a quarter of a century. This was his unified field theory, which attempted to set forth in one series of mutually consistent equations the physical laws governing two of the fundamental forces of the universe, gravitation and electromagnetism. So, yeah, here from our reading from out of my later years, it was kind of that was to be reflected that when he says this in an inertial system and a differential system, and then it's with regards to that having to be like an integral system and continuum mechanics, that Einstein's unified field theory would be a continuum mechanics for sure. That's then kind of the course here and what's being considered as to how and why things should be so. Dr. Einstein, the significance of this task can be appreciated only when one realizes that most of the phenomena of our external world seem to be produced by these two primordial forces. So here, that's framed that there's that, well, light speed is just so fast, and then and superclassical that way, and the nuclear and radionuclear is just so slow that it just happens to be that gravity and the electro, here it's read as the electromagnetic, but here is like the electrostatic, the electromagnetic, the electrodynamic, that it's electrodynamics is what it gets in the thing, because the magnetism is only ever kind of after there existing a field, that the field has to interact with something, and the field interacts with matter in accordance to its usual organizations as with regards to this tetrad of quantities, that then for the unification it's not so much there's just like, is there mass or is there charge, is there matter or is there electricity. There's also the idea that it's a tetrad of quantities, not just these two, and then as with regards to the three main interactions, say, or the legs of the hypergeometric and about 0, 1, and infinity, or there being three space dimensions, that those are different kinds of things that get into that then the theory of relativity itself, that motion is relative among frames, vis-a-vis that motion is absolute in like a static space. It has that that's the only thing that relativity really is and says, and then as with regards to how then we have a field superimposed that electrical field and the magnetic field, and then we have a gradient according to gravity, and then all the kinetics of matter and motion is either by that or it isn't, and here that it is, for mass and charge and its quantities, and then the velocity of light and the lifetime of the nucleon, that those kind of help affect the other parts of like the stopwatch and the meter stick. It's like seconds per meter and meters per second, as it were. Or seconds in meters per second, as it were. Until 100 years ago, electricity and magnetism, while known and studied since early Greek times, were regarded as separate quantities. Then that's the idea that, well, yeah, Maxwell makes for E and B and D and H that they come together and that they're crossed, and so it's great because it's possible to just draw their field lines and then draw the opposite tangent field lines, and it's great because that's both of them. But then on all the edges and on all the higher and lower orders, then they do fall quite right apart, yes. The experiments of Oersted and Faraday in the 19th century showed that a current of electricity is always surrounded by a magnetic field. And here is from reading from this O.W. Richardson's electron theory of matter. There's a number of different kinds of displacement current, true current, and all these other kinds of electrical current that are parts of these things. From these experiments came the discovery that the electromagnetic field, through which light waves, radio waves, and all other electromagnetic disturbances are propagated into space. So here we have that, well, that they all have kind of like a frequency and a wavelength because they have a wave model, but then calling that always electromagnetic radiation has that, no, they're not always considered exactly the same. And then also as to how they propagate in space is not the same, because there's space frames and frame spaces. And so one's about kinetic and that a kinetic massy body of matter is an extended body, and then according to our nuclear model, it's mostly space. And so when it moves, it kind of brings a space with it, as with regards to all the issues of space contraction, linear, and space contraction, rotational. Then the idea is that the electromagnetism, electrodynamics live in frame spaces for space frames, or otherwise that they're superimposed in all this one space-time field, all of it usually considered the geodesy and considered the kinetics and general relativities. Yet as well, though, that this is again part of this tetrad of quantities, and not oversimplifying stuff, because mass energy equivalency and charge energy equivalency and light energy equivalency and nuclear energy equivalency are all related in this milieu of that's being how the continuum of the conservation is to defining least action and least gradient for this sum of histories and sum of potentials, but that they're yet as well each their own things, as for example we read from Sedov. So and then so the author says, thus electricity and magnetism may be considered as aspects of a single force. In the classical, in the middle, in the pieces of the finite element analysis that add up to it, frozen at an instant in time, and otherwise, as with regards to that force has all the different ways here is from a couple episodes ago about the Poincaré completion, or as after the continuous functions, I suppose, was about that, and from continuous manifolds, is that having these kinds of ideas about how continuous manifolds can relate together, that it is a continuity, has it otherwise, having them as one force together has all these discontinuities and the pointy bits in this that don't line up. But the real continuum mechanics still kind of has them to be at one force, to be at one flow, to be at one flux, has that there's always an opposite, and so that just goes to show that at the same time it's a remarkably wonderful severe abstraction and electrical reduction, kind of like for mechanical reduction and electrical reduction. Maxwell's laws is that then there's also the superclassical aspects of Maxwell's laws, and so again, if this is a popularization. Save for gravitation and the newly discovered little understood meson forces, which appear to hold the various parts of the atomic nucleus together. So this would be about meson forces before they got up to quarks and gluons, and so and then about muon physics and then mesons and hadrons and that whole bit. So mesons and hadrons are like in Higgs theory is like, well, in Higgs theory, what's a meson? It's like, what's a meson? And, it is with regards to, well, we have a standard model. It's like, what's the standard model? It's like, well, remember all the exotic particles from particle physics in the 50s, 60s, and 70s, like skyrmions or something like that? Well, yeah, it's like, well, they don't live in the standard model. It's like, oh. But we do have bosons and in these kinds of things, and we do have in a little corner of the electromagnetic, according to our $1 billion giga electron volt particle collider, some numbers, and we kept looking, and eventually we found something that looked like the cent right shape, and called it a Higgs boson. I'm not trying to just cast shade on the Higgs boson, except it's not the theory. It's just a field. So anyways, these meson forces are another kind of idea of the theory, and maybe it's obsolete, maybe it's even antiquated, or some of its stipulations or necessary assumptions could no longer be said to hold. But so I'll be looking into mesons a little bit more as with regards to muons. Nearly all other forces in the material universe, frictional, chemical, cohesive forces, elastic forces, are of electromagnetic origin. They involve the mass C and the charge, yes. for all of these involve the interplay of matter, and all matter is composed of atoms, which in turn are composed of electrical particles. They have a charge, they have a mass, they have these quantities, and then the theories are like so. Yet the similarities between gravitational and electromagnetic phenomena are very striking. It's inverse square. And then to explain things like, well, why doesn't everything just fall together? The positive and negative just run right into each other. It's like, well, there's orbits and orbits and these kinds of things. And so you might have to think about an atomic model as different. It's like half and half in these cases, because the masses are considered very asymmetrical, while the charges are considered perfectly symmetrical, and this kind of thing. And then all the quantum theory, then in the rise for like, well, we had to throw out determinism to get a probabilistic view of things as random variables, and relations of random variables for the probabilistic setting, and ever since the Copenhagen conference, which defined what it was going to be because somebody had come up with a way to scratch that out. And it's like that's considered not part of this greater like real wave function, or Bohm to Broglie, as with regards to that being very well held up today, and that the continuum mechanics and the causal behind these things is a lot better held up today than what they're trying to figure out at this time. Let's just talk to me. He's an electrician, kind of. Although many attempts have been made to identify gravitational attraction as an electromagnetic effect, all have failed. Einstein thought he had succeeded in 1929 and published a unified field theory, which he later rejected as inadequate. His new theory, completed in the final days of 1949, was far more ambitious, for it promulgated a set of universal laws designed to encompass not only the boundless gravitational and electromagnetic fields of interstellar space, but also the tiny, terrible field inside the atom. Whether the whole grand objective of a unified field theory will be realized only many more months or years of mathematical and experimental work can determine. But in its vast cosmic picture, when fully revealed, the abyss between macrocosmos and microcosmos, the very big and the very little, will surely be bridged, and the whole complex of the universe will resolve into a homogeneous fabric in which matter and energy are indistinguishable, and all forms of motion, from the slow wheeling of the galaxies to the wild flight of electrons, become simply changes in the structure and concentration of the primordial field. So this is Lincoln Barnett is saying, oh, wow, this is kind of like getting to your mathematical universe hypothesis. Although when matter and energy are indistinguishable, I'll disagree with that. It's just saying that there's fundamental rules about them, but it's still like any one particular one is an individual and it's distinct. And then all forms of motion, and here is about the, he talks about galaxies being slow, and it's like, well, in their own frames, they can be pretty much as fast as they go. And the wild flight of electrons is like, well, maybe electrons are just in little orbits themselves. We think of electrons as orbiting things, but what if they're just very lopsided orbits themselves? This is that everything is in orbits, not in the geodesy and the world lines. That all true world lines are orbits is the idea. Yet this is pretty agreeable. Then thinking it's like, well, if we can figure out from axiomless theory and axiomless geometry a real natural continuum that kind of shows up for a hologrammatic or holographic way to describe, then in these mathematical resources of geometry and numbers, then the space and time would naturally be like that. That however that goes, we got to arrive at inverse square law for gravitation and inverse square law for attraction, the model of attraction in the classical, because everything is according to that pretty much. That's the rule. And then here the idea is that, and then that's the classical side. The actual sum of potentials from the outside is a fall gravity. That it results that in the middle, and then that the physical constants are defined like how far apart are these things, how much volume in like the gas law and these kinds of things, kind of working backward from what's built up after the inductive of like the gas laws and volumes and molecular forces and these kinds of things. As with regards to after something like light speed, then all the behaviors of quantities in electromagnetic and their velocities, which are not, according to Huygens principle and the L principle, a constant. And furthermore, in many derivations, kind of like are these other values of C, this constant, from electromagnetism and electrodynamic theory above and below the light speed. Since the aim of science is to describe and explain the world we live in, such a theory would, by thus defining the manifold of nature within the terms of a single harmonious theory, attain its loftiest goal. The meaning of the word explain, however, suffers a contraction with man's every step in quest of reality. Science cannot yet really explain electricity, magnetism, and gravitation. Their effects can be measured and predicted, but of their ultimate nature, no more is known to the modern scientist than to Thales of Miletus, who first speculated on the electrification of amber around 585 BC. Most contemporary physicists reject the notion that man can even discover what these mysterious forces really are. Aristotle, whose natural science dominated Western thought for 2,000 years, believed that man could arrive at an understanding of ultimate reality by reasoning from self-evident principles. So here it's a there or none, and that's about it. And so then this is well known as what's called the fundamental question of metaphysics. Why is there something from nothing? After why is there something rather than nothing? Why is there something from nothing? And then we talk about explanatory factors and these kinds of things. So this would be a great little book, but what I'd like to see is something kind of about what there is a super classical vis-a-vis otherwise just the continuum mechanics and the usual things. To understand the significance of this retreat, it is necessary to step across the thin line that divides physics from metaphysics. Questions involving the relationship between observer and reality, subject and object, have haunted philosophical thinkers since the dawn of reason. So here it's figured it's going to be okay. Yet it is well that there's a very strong and reasoned account as to why it has to be great to be okay. And he talks about space, philosophical subtleties. And so that reminds one of Descartes and subtle matter, or Leibniz and subtle matter. Prisms, radiation, rays, infrared. He's got visible light here between the unknown and cosmic rays with the very small wavelength, gamma rays and X-rays in the ultraviolet, and then infrared heat waves, spark discharges, radar, television, short radio waves, broadcast waves, longer radio waves. See, this is funny because it's got like a double power series off of each side of the visible light with regards to the rays and waves and heat, because heat just results heat, and then all that stuff does not result heat. I guess you got the microwaves, spark discharges is he's got there, and X-rays. So anything outside of the optical spectrum is spark discharges or X-rays here. So I'm going to have to follow up a little bit more on that, trying to sort out what's going on with the dual tri-stimulus color space and properties of the aspect of free information, that's signal and information, signal theory, and physical image theory. About the quanta, Planck and the quanta, here the idea is there's like a superquantum and a subquantum, which is just like it's smooth again, it's continuous again. Vis-a-vis the quantum, it's like this is a finite classical quantity, the quantum. In any process of radiation, the amount of emitted energy divided by the frequency is always equal to h. So that basically defines what frequency and wavelength is in radiation. It's just whatever h, Planck's constant, says that it adds up at the atomic scale. Like other universal constants, it is simply a mathematical fact for which no explanation has been given. See here, for example, we're kind of breaking that down a little bit. That Planck, yeah, there's much to be made from Planck's, and the making of the finite from the infinite. And then in his complement, Bohm and de Broglie, where Broglie is like, remember how all these things are particles, really? They're still waves. And so then again, there's still resonances. And the action at a distance means actually it's just something infinite happened. And it happens all the time, everywhere. And so that's perfectly natural. The far-reaching implications of Planck's conjecture. Planck was, quantum mechanics was picked up by many scientists because they will say, look, I just made this into a discrete problem and I found a solution. Can I have a Nobel Prize? Because they'll have found something with that. He expressed these principles in a series of historic equations which won him the Nobel Prize and profoundly influenced later work in quantum physics and spectroscopy. If there's a joke about like what's the only physicist that anybody knows, it's like, was it not Einstein? And the other one is like Nobel Prize winners, because it's figured just like, well, somebody knows. They put a lot of money into that. They're spending money on it. Maybe those are the scientists. And thus adducing an important new physical principle, Einstein uncovered at the same time one of the deepest and most troubling enigmas of nature. No one doubts that all matter is made up of atoms. Although you can ask Einstein, he's like, are atoms real? He's like, yeah. Is matter made up of them? He's like, yeah. And it's like, what are they made up of? It's like, meh. Which in turn composed of even smaller building blocks called electrons, neutrons, and protons, and as with regards to their interactions with photons, that in nucleons could be seen as so related with regards to balancing out the photons. And then we talk about particle theory and the usual ideas that came into the theory. And he gets to talking about positivists or logical empiricists. So here that's about logicist positivism and why that's not a weaker thing, but only a stronger thing, and then the weaker thing isn't necessarily a thing to what it would be. And that's part of the philosophy, but we can eventually give that as part of a mathematics, and then the physicists would be like, well, yeah, I have to observe that because it's a mathematical physics. And then he talks about Locke. On his great treatise on human understanding, philosopher John Locke wrote 300 years ago, a company of chessmen standing on the same squares of the chessboard, where we left them, we say, are all in the same place or unmoved, though perhaps the chessboard has been in the meantime carried out of one room into another. The chessboard, we also say, is in the same place if it remain in the same part of the cabin, though perhaps the ship which it is in sails all the while. And the ship is said to be in the same place, supposing it kept the same distance with the neighboring land. Perhaps the earth is turned around, so chessmen on board his ship have everyone changed place in respect to remoter bodies. Embodied in this little picture of the moving but unmoved chessmen is one principle of relativity of position. But this suggests another idea, relativity of motion. And so then this just gets into that relativity theory is kind of like so. So I'll look at this some more, and what it addresses is it helps to address, to popularize a lot of different concepts that are already here, kind of just part of the context. And so then as with regards to them and about how they are is kind of like so. Several theories. Gravity. Unified field theory. The phone is low. uncharged. So if I missed a few things there, it was basically saying that the popularization, like Lincoln Barnett's, helps introduce a lot of the concepts here, which are part of the real physics, this philosophy of the physics. And then a model physicist, eventually, if you're giving him a mathematical physics that embodies also the philosophy of the things, then he has to follow that, which is pretty great. So this is a book by Carl Boyer. It's A History of Mathematics. It's got Descartes in it. There's Leibniz, it looks like. All these different people on there. Maybe some of the Bernoullis. It's got a foreword by Isaac Asimov. It's A History of Mathematics. It's revised by Udo C. Mersbach from John Wiley and Sons. Published in 1991. Talks about time, the cave paintings, the conates, Galen, one of the greatest of the ancient physicians. So people usually think of like, well, who's the ancient doctor? It's like, well, there's Hippocrates, but then Galen was in the Greek tradition, at least, is one of the most ancient ones. Vis-a-vis traditional Chinese medicine, traditional medicine, theory of humors, the organs in that. Now we can see what makes mathematics unique. Only in mathematics is there no significant correction, only extension. Now, that is partially true, because it's always like but that's like mathematics that's already consistent. So Boyer's definition kind of was like, and by that I mean if mathematics was ever wrong, it was not mathematics. It was just a mistake. And so that's kind of harsh seeming maybe, but it's at the same time, it's like, he's a strong mathematical Platonist in the sense that he would agree that mathematics has got something perfect about it. Once the Greeks had developed the deductive method, they were correct in what they did, correct for all time. Euclid was incomplete, and his work has been extended enormously, but it has not had to be corrected. His theorems are, every one of them, valid to this day. And sometimes this is said as like, the column circumference proof from 1400s is still good. Ptolemy may have developed an erroneous picture of the planetary system, but the system of trigonometry he worked out to help him with his calculations remains correct forever. Here there's also a system to be figured out of n-lateralometry, which is like, instead of taking a right triangle in a circle and then drawn out, and then the ratios opposite over hypotenuse and adjacent over hypotenuse make them for cosine and sine respectively, or as it so may be, if I'll remember, SOA, COA, TOA, and this kind of thing. That there's also a way to draw the same functions as by evolving all the angles at the same time, which is not available as a classical construction, but would be really mechanically simple as via like a pantograph or something like that. That is to be figured out. Nothing pertaining to humanity becomes us so well as mathematics. Then and only there do we touch the human mind at its peak. So this is just something we've read some histories of mathematics here, and so there are more of them. There are many more of them. Hertog's The Origin of Time, Stephen Hawking's Final Theory, offers insight into an extraordinary individual, the creative process, and the scope and limits of our current understanding of the cosmos. Well, we're up to the hour today, and it was saying this wonderful book about, now Hertog is basically, he worked pretty closely with Hawking in the 20th century. From like 1998, he said Stephen's colleague Neil Turok said to come meet him. Stephen's office. Blackboard's full of figures. Andre. I'll be looking at this. I'll be reading this to understand what's going on with this. This is just a Rudyard Kipling from 1898 called Plain Tales from the Hills. 1898. Well, good day, gentle readers. Happy New Year's.